So last time we probably only just talk about the one concept, which is enthalpy of formation. Enthalpy of formation. Okay, last time we talked about enthalpy of formation. So in general, enthalpy formation, what is the purpose of the enthalpy formation? When we introduce the enthalpy formation, this concept, the most important thing is scientists is really want to figure out the enthalpy of some of the reactions. The enthalpy of some of the reactions. This is what the scientists want to answer. Okay, for example, we have chemical reactions C2H6. This is an alkene. React with oxygen, then they're going to form CO2 plus water. All right, so we have let's balance this equation. 2, 3. Okay, so 3, that's a 7. That's a 2, 7, 4, 6. Okay, so now this is a chemical reactions. And we have those are gas phases for each of this. And the scientists, they really want to know what is the enthalpy of these reactions. Okay, so they want to know it. So they think about it. Is there any way, easy way we can predict what is the enthalpy of these reactions? How much heat the reaction will be produced? Okay, so that is why they think, okay, I mean, we understand actually the enthalpy of these reactions actually is just the difference of the energy between the reactant and the product. So if you know the energy for the reactant, and you also know the energy of the product, the difference of that will be just the enthalpy of the reactions. So they figure out, okay, how can we get the energy of this reactant or the energy of the product? Well, this is why they developed one of the concepts called enthalpy of formation. So generally, you're just the difference of the enthalpy of the reaction is just the difference of the enthalpy of the formation for the product and the reactant. Okay, so that is why we know the enthalpy of the reaction is the sum of the enthalpy formation of the product subtract the sum of enthalpy of formation of the reactant. So that is why. Okay. Yeah. So that is why if we know the enthalpy formation for each of this stuff, yeah, if we know the enthalpy formation for each of this, then we will figure out the enthalpy formation of the reactant, the reaction. So each of this guy will have the enthalpy formation associated with enthalpy formation of the water gas. Okay, so if we know enthalpy formation for each of the species, then generally we can figure out the enthalpy of these reactions. That's it. Okay, that's it. Then we talk about there's a concept that the enthalpy formation, this is the man-made concept. The people define there's something is 0, just like we define the sea level is 0 meter. Okay, the sea level, because enthalpy formation need to compare something, and that is the part that you're gonna compare with. The enthalpy formation is equal to 0, and what things is equal to 0 is those elements. The elements with the most stable form. At standard condition. And that is why we have a little circle over here, and this is called a standard condition. So this is called a standard enthalpy of formation. Okay, standard enthalpy formation. So those elements with the most stable form at standard condition is equal to 0. And people, students sometimes confused. Okay, how can we determine which is stable form, which is stable form? Well, just let you know, most metals, you see, look at it here. Most metals, those are solids, right? So sodium solids, this is a standard. This is the most stable form, other than sodium liquid, right? Or sodium gas. I mean, those two are not a standard condition, and this is not stable form. Because in the room temperature, definitely you're not going to have a liquid or gas phase for the sodium. That makes sense, right? Yeah. Well, there are 7 diatomic elements, right? 7 diatomic elements. And those guys, normally most stable form is just diatomic, okay? So like hydrogen gas, oxygen gas, nitrogen gas, fluorine gas, chlorine gas, bromine, and the bromine is a liquid in the room temperature. You see, here it shows the blue on here. The bromine is a liquid. Blue means the liquid, and black means it's a solids. Okay, so the iodine solids, that is the most stable form. You see, those gases are most stable form. But for most of the other condition is metal. The metal, most of thcases, is solids, right? Except the mercury. Mercury is a liquid in the room temperature. Make sense, right? Yeah. So those are all most stable form. Are you with me? Okay, yeah. So that's why the enthalpy formation of those elements, those are all solid, 0, equal to 0. That makes sense, right? Okay, and we also talk about there's a chemical reactions that are associated with an enthalpy of formations, right? So if you're talking about the chemical reactions for the enthalpy formation of certain, then you just need to remember. Okay, so what exactly the equation reactions associated with this? For example, once you want to figure out the enthalpy formation of the N2NO2, this is a nitrogen dioxide gases, then what is the equation associated with it? And you gotta remember, this is talk about a formation, right? Formation generally is just to form, right? So we're going to produce to form. So to form how many of the nitrogen NO2? We're going to form 1 mole of NO2. So in this equation, there only have 1 moles of the NO2. So this is for sure. You're going to form 1 moles of the NO2. And then they're going to come from some of the reactant. And what is the reactant? Again, the reactant will be those elements with the most stable form. Okay? So there's 2 elements over there, right? Nitrogen and oxygen. So you're going to have a nitrogen and oxygen involving these reactions. And that's going to be the most stable form. Okay. Now, what is the most stable form for nitrogen? Well, nitrogen gas is N2 gas. What is the most stable form for oxygen? O2 gas. Right? Then you're almost done. So you have the 2 reactants, then just need to balance these equations. But you need to make sure you need to have just 1 mole of the NO2, which means you're gonna have 1/2 on the coefficient for the nitrogen and just 1 on the coefficient for the oxygen. Then this equation is the equation that associated with the enthalpy of formation of the NO2 gases. NO2 gas, that's it. Okay. Well, then let's just talk about, give you another examples. So if we talk about enthalpy formation of the sodium chloride solids, then what are we gonna do? Well, again, you're going to form 1 mole of the sodium chloride. Okay, you're going to form 1 mole of the sodium chloride solids. And then they're going to coming from their reactant. The reactant must be the elements that form this compound, right? So the elements that should be sodium and the chlorine. And those elements must be in their most stable form. And obviously sodium is just a sodium solids. And the chlorine is a Cl2 gas, chlorine gas. And then you add them together and then balance these equations. So that's the equation should be 1/2 of here and put a 1. And this is the chemical reactions. The chemical reactions of this reaction, the enthalpy of this reaction will be just equal to the enthalpy formation of the sodium chloride solids. That's it. Okay. Well, then we can talk about one more. Okay, so what is the enthalpy formation of the sugar C6H12O6 solids? This is cane sugar. Okay, then again, you're going to form 1 mole of these molecules. So 1 mole of the C6H12O6 solids. Okay, you're going to form 1 mole of this. And then where this come from? Coming from their elements, and those elements must be their most stable form, which is the carbon, hydrogen, and oxygen. So hydrogen we know is H2 gas, oxygen is O2 gas, carbon that's going to be solids, and obviously they are not just the solids, it's graphite. Then you add them together and then balance the equation. So now we're gonna have a 6 carbon and a 6 hydrogen gas and 3 oxygen gas. And this equation, the chemical reactions, the enthalpy of these reactions will be equal to the enthalpy formation of the C6H12O6 solids. So that's it. Okay, so this is enthalpy formation is the equation associated with the enthalpy formation. It just form 1 mole of this compound. And the reactant is coming from their elements. And the elements must be in the most stable form. Does that make sense? Okay, yeah. So generally, this is what we learned last time. And today we're going to talk a little bit more. Okay, we're going to still talk about the enthalpy of the reactions. Okay, and scientists really want to figure out the enthalpy of the reactions. Doesn't matter what kind of reactions. There's another way the scientists find. Okay, we're still going to find the difference, the energy difference between the reactant and the product. But there's another difference. Other than the enthalpy formation, the scientists find another difference, which is using the bond energy. It's called the bond energy. Bond energy. So what exactly is a bond energy? Have you heard this term, bond energy? Not exactly, huh? Yeah. So what exactly is the bond energy? So first, let's see what is the bond. We will talk about more when we talk about unit 4. But the bond energy is talk about the energy that between 2 molecules. For example, the hydrogen and another hydrogen. So the hydrogen and hydrogen, this is hydrogen atoms, and this is hydrogen, another hydrogen atoms. They're going to have an invisible bond connect together to make the H2. Okay, if there's no bond, for those hydrogen, then we can only say this is two of the hydrogen atoms. But if they have a bond, then they are going to the two hydrogen atoms making a molecule become H2. Okay, so that is a bond. This is a bond, what we are talking about. So what exactly is the bond energy? The bond energy means, well, we want to break the bond. We try to break the bond between the two hydrogens to making two of the single hydrogen atoms. To make two single hydrogen atoms. Then how much energy that we need to require to break the bond? Okay, how much energy that we require to break the bond? And this energy is what we call the bond energy. Just like, okay, so now we have a string over here. This is a rubber band, okay? It's not, we have a rubber band. If we want to break the rubber band, what we need to do? We have to stretch it, right? We have to apply our force. In another word, we need to apply the energy to break the bond, to break this. That makes sense, right? So chemical bonds is the same thing. If you want to break the chemical bonds, you have to apply the energy. In another word, this is the endothermic process. This is endothermic reactions. Okay, yeah. So you need to apply the energy on this to break the bond. So the bond energy is just equal to the energy that is required to break 1 mole of these bonds. So this is the bond energy that we talk about. And just to let you know, different bonds, when you break it, they are require different energy, right? Different bonds, when you break, they require the different energy. But then if you have a sum of the compound, if you have a sum compound like this is a methane. This is a methane. This is a CH4 methane. And the structure of the methane is like this. So if you're looking at here, this guy has 4 bonds. And those are 4 bonds are all 4, they have a 4 of the carbon and hydrogen bonds. It makes sense, right? So that makes sense, right? So this guy has a 4 of the carbon and hydrogen bond. And then we can just assume the energy for this methane, this compound, is just the 4 of energy 4 times the carbon hydrogen bond. That's it. This is the energy that is stored inside of this methane. That makes sense, right? Okay. And if you were talking about the chlorine and the chlorine bond, which is the Cl2, Cl2 that's made by 2 chlorine atoms. They are just to have 1 bond. So the energy that for the Cl2 is just a Cl-Cl bond. Makes sense, right? And if we have something like oxygen, the oxygen is something like that. The oxygen has a oxygen double bonds. They have a double bonds over here. So the energy that between for the oxygen gases, then that's just the double bonds shows up there. That makes sense, right? The energy that's stored in this. So that is why we can just using the difference between the energy in the reactant and the product to figure out the enthalpy of the total reactions. Okay, yeah. So that is why the enthalpy of the chemical reactions can be rewrite, but this one is a little bit different. Can be rewrite as the bond energy of the reactant subtract the bond energy of product. Okay, so this one is different. This one is different from the enthalpy of the reactions. Enthalpy of the reaction is the product minus the reactant, right? But this one, the bond energy, if you're talking about bond energy, then that's a product, the reactant subtract the product. Okay, so this is the only difference when we talk about the enthalpy of the reaction. We're still talking about enthalpy of the reaction, but this one is the bond energy of the reactant subtract the bond energy of the product. But when we talk about enthalpy formation, that's the enthalpy formation of product subtract the enthalpy formation of the reactant. Okay, yeah. So let's talk about one of the example, which is in the page 7, question number 8. Okay, so let's looking at the page 7, question number 8. Page 7, question number 8. So here is talking about we have the reactions is N2 gas react with 3 moles of the hydrogen gas, and then they're going to form 2 moles of the NH3 gas. Okay, so so this is the chemical reactions, and we try to figure out what is the enthalpy of these reactions. Well, they're going to give you a list of those bond energies. But the point is, the very important thing is you need to know what is the structure of these molecules. Okay, without knowing the structure of the molecule, it's hard for you to make the calculations. So since we haven't talked about the Lewis structure over here, I will draw the structures. And in the exam, I will also show the structures for you. So you will just looking at the structure and understand how much what's the bond energy inside of the molecules. For the nitrogen, the structure is something like this. This guy has a one triple bonds. Hydrogen is just a hydrogen single bonds, but this guy has 3 of the hydrogen. So we have 3 of the hydrogen single bonds. Ammonia is a little bit complicated. So nitrogen in center, hydrogen is on the side. Okay, and they have a 2 of the ammonia over here. So let's looking at here. So we can just make a summary. In the reactant, what's the energy? What's the bond energy that we have? We're having 1 of the nitrogen triple bonds, and we have 3 of the hydrogen single bonds. This is what we have for the reactant. For the product, now we are having just you see nitrogen is connected with hydrogen, 3 of the hydrogen, and each of this they are having a bond. So this guy has the nitrogen and the hydrogen bonds, and you see all of those are nitrogen hydrogen bond, right? All of those 3 bonds are all nitrogen hydrogen bonds. And so for 1 of the ammonia, we have 3 of the nitrogen hydrogen bonds, and since we have 2 of the ammonia, which means that's 3 of these bonds, and you also gonna times 2. So totally we have 6 nitrogen and hydrogen bond. That makes sense, right? Okay, so now those bonds generally, and the bond energy between those bonds is the energy that inside of those molecules. Okay, so based on this equation, the enthalpy of these reactions is the bond energy of the reactant subtract the bond energy of the product. Then generally we can figure out the enthalpy of these reactions. So the enthalpy of the reactions will be just equal to the reactant minus product in this case. The bond energy. So the bond energy for 1 of the nitrogen triple bonds, you have N4 6 and for 6, this is a kilojoule per mole. And you plus 3 of the hydrogen bond. And this is a 3 times 435 kilojoule per mole. And this is what we have for the reactant. And you subtract how much you have for the product. You have a 6 of the nitrogen-hydrogen bonds. So 6 times nitrogen-hydrogen bonds over here. So 6 times nitrogen-hydrogen bonds. That's going to be 398 kilojoule per mole. So the result of this will be the enthalpy of these reactions. Okay, so 946 plus 3 times 435 and subtract 6 times 389. And you got negative 83. So the negative 83 will be negative 83, that's kilojoule per mole, will be the answer for the enthalpy of these reactions. Okay, so generally you're doing the mostly the same thing for the enthalpy of formation. The only difference is this one bond energy is a reactant minus the product. It's not the product minus reactant. Okay, so now it's your turn to do the practice. Let's work on the question number 10. I will write down the structure for those compounds. So the methane is just a carbon inside and hydrogen on the side. Chlorine is just Cl. This CH3Cl is this one. Hydrogen is just HCl. Okay, so now you're going to base on the structure over here to figure out, okay, what kind of the bond energy that's stored in those compounds, and how much energy that for the reactant, how much energy for the product, and find out what is the enthalpy of these reactions. All right, so let's looking at this. Again, you just need to recognize, okay, what kind of a bonds between this compound. So obviously this guy has just one single kind of bond, carbon and hydrogen. They have 4 of them, so you times 4. This guy, we have one of the chlorine and the chlorine gas. And this is what we have for the reactant. You subtract what we have for the product. And here you have 3 of the carbon and hydrogen plus 1 of the carbon chlorine. So this is what we have for this compound. And plus the hydrogen and the chlorine bond. So once the difference between those will be the enthalpy of the reactions, the enthalpy of the reaction. So what you need to do is just plug those numbers over there. 4 times carbon and hydrogen, so this is a 410, and this one is 239. This one is still 410. Carbon chlorine 327. Hydrogen and the chlorine will be a 427. Okay, so now you add them together will be the result. The result is just negative 105 kilojoule per mole. Does it make sense? Right. So here is the only thing that you need to care about. The only 2 things you need to care about. First one, this is a bond. When we talk about bond energy, that's a product minus reactant. Second one is you need to based on the structure to see what kind of bond they have. Okay, and then just choose the correct bond energy. That's it. Okay. All right, so this is pretty much I'm going to talk for the thermal chemistry. for the thermal chemistry. And later, let's take a break. And after that, we will talk about the chemical, we'll be talking about the gas. Okay. And by the way, you don't have to turn in the lab report. So we will turn in the lab report in the next class. Okay, so let's come back. Next part, we're going to talk about the gas. Gas. Well, gas is one kind of the state, right? Important state in the in a substance. Okay, but when we talk about the gas, it's different from the solids and the liquid. Gas is a little bit different. Okay, because so if you compare with the solid, liquid, and gas, for the solids, we know when we determine the solids, we determine their mass, and also we're going to determine its shape and volume. So each of the solids, they have their definite shape, and also they have a definite volume. But for the liquid, well, we know we do have the volume, right? You can measure the volume of a liquid. So the liquid, they do have a definite volume, but the liquid do not have their definite shape. The shape of the liquid is really depends on the shape of the container, right? What kind of container you're holding it. If there's no container, then that's just a splash. That's just a pond, little small pond. on the ground, right? So the shape of the liquid is really depends on what kind of container it is. So that depends on the shape of the container. For a gas, well, the gas, they don't have a volume, they don't have a content, they don't have a shape. You may think about it, hey, gas, why the gas don't have a volume? Well, gas volume is really depends on, they do not have, they do have a volume, but they do not have a fixed volume, which means the volume of the gas is depends on the volume of the container. Same amount of the gas can be that big if you have a really big container. Can also really small if you have a smaller container. Okay, so they do not have a definite shape and also do not have a definite volume. So they have a no definite shape and volume. So that's the difference between solids, liquid, and gas. So, and that is why when we determine gas, we need to have a more additional parameters. Okay, for example, when we determine gas, we need to using 4 different parameters: pressure, temperature, volume, and the mole of gas. So the P is the pressure, T is the temperature, V is the volume, and N is mole of gas. Okay, N is a mole of gas. So that is the difference. Yeah. P, T, V, N. So we're going to using 4 different parameters to determine gas, not just the several. For the solid, probably just using mass and the volume. Then that's it. Okay, but this gas you need to using more. Okay, you're using more. So we already talked about the temperature, volume, and mole of gas. Okay, we know the unit, but let's first talk about the pressure. Okay, what is exactly the pressure? The pressure is equal to a force applied on certain area. Okay, so a force applied on an area, which means you may have a force and you apply a very small tiny area, then that is a pressure. Or like just once you're, so that means if you have something, I'm using force to poke my arm, okay? You didn't feel too much pain, okay? But if I'm using the same force and push the needle on your arm, then that's gonna be really pain, right? I mean, the force is the same, but we narrow down the area that apply that much of force, it will increase the pressure. Does that make sense, right? Okay, yeah. So this is, your feel pain is not because of the force, it's because of the pressure. Okay, high pressure, then you will feel pain. That makes sense, right? And what is happened for the pressure on a gas? How come the gas can have a pressure? Well, then you need to think about it. Okay, in the micro scale, I mean, what is this gas molecule? You remember, gas molecule flying everywhere right now. It just keep bumping something. Okay, so the gas molecule is just constantly hitting a board, right? When they hit on the board, then they bounce back. But they are going to apply a force on the board, right? And then the pressure will be generated. And remember, we have tons of the molecules, gas molecules. So the gas molecules keep continue bounce or hit the board. So that's why the pressure generated. And we have a 1 atmosphere pressure, right? And that is pressure is applied on our shoulder. And this is because the gas molecule keep continue, heat our body, right? And if you have a wind, remember, if you have a wind, well, how come we have a wind? The wind is just a gas molecule fly, keep heating your body. So if the wind is big enough, you will be blown away. Why? Because gas molecule, the force is strong enough, so it can push you back. Okay, yeah. So this is what happened. So that's why, and this is what happened for the pressure. And then what is the unit for the pressure? Unit of pressure, and in chemistry, in the SI unit, we're using Pascal. Or PA to represent the Pascal. Okay, so that's a unit. But this unit is really small. The unit of this is a Newton per, I think it's Newton per centimeters, Newton per centimeter square. So that is the unit for Pascal. One of this Newton per centimeter square. But this unit is really, really small. We're not going to use using this unit, okay, in chemistry. Most of the cases we're using atmosphere, ATM. So atmosphere. So 1 atmosphere is generally the normal pressure that's applied on our body now. Okay, so, and also Earth usually has a 1 atmosphere, the pressure. Okay, the Earth, the environment has a 1 atmosphere, the pressure. So the 1 atmosphere is equal to 1.01 times 10 to the 5th Pascal. You see, so that's why we talk about the Pascal is really, really small unit. We're not going to using this unit. And there's another unit, it's called a bar. And this bar is not the bar that you went last night. Okay, so the bar is also a unit, but very close to atmosphere. It's 1.0 times 10 to the 5th Pascal. You see, this is 1.01, this is 1. So very close to each other. 1 bar almost equal to 1 atmosphere. Okay, yeah. So that's a bar. And another unit is called millimeter of height of mercury. Anyone heard of this unit, millimeter height of mercury? Owen, where did you go? Hear that?
It's like old thermometers.
This, yeah, that's true. Wait, old thermometer?
I think, yeah.
Or
Temperature change.
it's not thermometer, but I mean, this is an old unit,
Will do.
and people using mercury as an indicator. Okay, so millimeter height of mercury is pretty old unit, but currently not so many people using this unit. But when I learning this, the physics, we're still using millimeter height of mercury. Okay, so the millimeter height of mercury, and especially when at the 80s, yeah, when you measure your body, what's that called? The pressure in your body, the blood pressure, they're using millimeter height of mercury. I mean, they're still using that unit. So just telling about a little bit history of this. Okay, this is an old unit like it happened in 1800s. Pretty old units. Okay, so and this is originally coming from British, coming from Britain. Okay, so what happens? I mean, one, the scientists they try to determine the pressure in the air. Okay, try to determine the pressure in the air. So they apply they generate one of the device. And it's pretty simple device. They're just put a container over here, and this container is opened. They put quite a lot of mercury over there. So this is a mercury. They put a mercury over there. Okay, and then what they do, they put a tube inside of the mercury. They put a tube inside of mercury, but this tube is a vacuum tube, which is they suck everything out of this tube, which is this guy is a vacuum. So once the vacuum is put inside of this mercury, and since we have a pressure coming from the air, the pressure of the air will push the mercury up. Will push the mercury up to a certain level. And then the height, generally the height of the mercury, and that's going to be equal to the pressure of the air. Because the reason we can lift up the mercury is because of the pressure. The pressure pushed the mercury. Then they're going to reach to an equilibrium. And that's equilibrium. So that's why the height of the mercury can represent the pressure of the air. Okay, so that is the reason where I got the height of mercury. This is a millimeter height of mercury. And the people using the height of mercury to represent height of the pressure of the air. Okay, so generally this is why. And this unit, I mean like a 760 millimeter height of mercury is equal to 1 atmosphere. Okay, yeah, 760 height of mercury is equal to 1 atmosphere. I think I can search online to find a yeah, you see. So this is what happened. They're putting the mercury underneath. Okay, then they put the a bar over there. So the vacuum is over here. The atmosphere press the mercury and push this up. The height of this will be just the pressure of the air. That's it. Okay, so millimeter height of mercury. This is a pretty old units. Yeah, this is a pretty old units. Okay, so that's why currently you're not you're not heard of the millimeter height of mercury. Instead, the people using another name to call the millimeter height of mercury, which is a torr. They're using torr instead of the millimeter height of mercury. So the torr and the millimeter height of mercury is exactly the same. 760 torr is equal to 1 atmosphere. Okay, 760 millimeter height of 760 torr is equal to 1 atmosphere. So those two are interchangeable. The last unit we're going to introduce is a PSI. I think you're gonna familiar with this. What is a PSI for? What is a PSI for? What is the full name for the PSI?
Pressure.
It's a pound per square inch. Okay, so remember the pressure is a force over the area, right? So that's why this one is a pound. Pound is a force, right? And over a square inch. Pound over square inch. And this is a PSI. So this is a 1 PSI. 1 PSI is 1 pound per square inch. So 14.7 PSI, that's equal to 1 atmosphere. Okay, 14.7 PSI equal to 1 atmosphere. Usually, the tire of cars, you need about like 33 PSI to 35 PSI, right? So you can think about it. It's about it's about like a 2.5 atmosphere. So the pressure of the tire is pretty strong. It's about like a 2.5 atmosphere. So I'm going to show you one of the, so what exactly, visualize what exactly is 14.7 pound per square inch. Okay. So this is, if you're looking at it here, this bar is 14, right? Is a 1 square inch. This is an inch by inch, the metal bar. Okay. So this area is 1 square inch, and this whole bar is a mass, the weight 14.7 pounds. So that means if you apply the weight of 14.7 on the 1 atmosphere, and the whole thing is a 1 atmosphere pressure. Anyone want to try and how much pressure that apply on the finger? I tried it. I mean, it's okay. You see, I put in my hands. Anyone can help me? Yeah. Okay, so just put the height apply on one of my finger. Yeah, it's not that bad. I mean, I can stand with it. Okay, I feel uncomfortable, but it's still okay. So anyone want to try? Not that hard. Okay, so that is just a 1 atmosphere. Okay, 1 atmosphere. It's not that bad, too much. And if you double it, and that's gonna be 2 atmosphere. Okay, then that's gonna be hard. Okay, let's apply too much pressure on the part. Okay. Okay, so here is the unit for the gases, for the unit for the gas. And then I would like to talk a little bit more about the gas, liquid, and the solids. Okay, you probably didn't recognize. Okay, every substance, pure substance, they're going to have their 3 different phases, right? They have a gas, they have a liquid, and solids, just like ice, water, and vapor. Okay, so what exactly happens? Why the molecules? I mean, I would like to talk about the process of from solid to liquid to gas, compared to our life. Okay, this is a physiologically comparison a little bit. Okay, so what that mean? The solids. Why we have a solids? Solids. I mean, in another word. So remember, those are molecules. We can just think those are molecules. The molecules, when they are going to be a solids, then they're just aggregated together, okay, to align together, and then know where to go. I mean, we generated the crystal, right? You see the crystal. Those molecules are just stuck together. I mean, know where to move, or it's really hard to move. There's an invisible force that holding the molecules, know where to go. Just like when you're a baby, okay, your parents. I mean, you have the relationship between you and your parents, but at that time, the baby has a less mobility, and the parents generally has a much force holding the baby, right? Yeah, so the baby has a less ability to move around. Did you anytime when you go to the mall, when you went to the mall, did you see some of the baby wear the backpack, and then the parents have the leash with it? Do you see that, right? Yeah. But the molecules, they're having an invisible force, invisible line holding the molecules, know nowhere, go nowhere, okay?
And so this is solids. And what happened for the liquid? Liquid, then that means I mean the molecules is there's a little bit of space for each of the molecules, and the molecules has a space to move around, just like when you go to the teenager. Okay, well, you still have the relationship and the
Connection between your parents and present you. Those connection is not changing anything. But the only thing that change is you. You grow up. You have a kind of like energy. I mean, against the force. Liquid is doing the same thing. Okay. Each of the molecules, when the temperature goes up, they have become hard kinetic energy. So they start to against the force between the molecules. So that's why they're going to have a space to move around. Okay, they still have, but they still be constrained by the force, but they have ability to move around, just like you're
in a teenager. And what happens when you go to the gas phases? When you go to the gas phase, I mean, generally the force is still there. Okay, you and your parents still have the force, but you grow up. You have a full ability, and you have a full ability to move. Okay, generally the force between the molecules is much weaker than the activity energy of those molecules. So that's why they start to move around, and then they are going to far away from each others. Okay, move far away from each others. And generally, those connection or those force between the molecules is much negligible compared to the ability, the kinetic energy for each of the molecules. That makes sense. So that is the difference between solids, liquid, and a gas. Right? I mean, I had a student talk about, well, where are you now? Are you gas? Are you solids? Definitely you're not solids. And are you liquid? Where are you now? And I had a student said, okay, we're gas, but will the gas still pay the gas? We're still going to pay the gas. So that is why you got it independent.
Okay, so hopefully this will help you to understand the three different phases: solids, liquid, and gases. Okay, solids, the force is strong. The activity of the molecules is weak, so that's why they are not moving. But the liquid, the force is still the same, but the activity of the molecule getting hard, so that's why start against. They have a space to move. Gas molecule, again, the force is still the same, but the activity of the molecules is much stronger than the force, so they are free to move around. That make sense? Okay, yeah. All right, so let's come back. The next part, we're going to talk about a gas law. But today, since we don't have enough time, I'm going to just introduce one gas law. We have several different gas law over here we need to introduce. But today, I'm going to just talk about the one. It's called the Boyle's law. I hope you're going to remember the name. Okay, Boyle's law. You're going to remember the name and also remember what is the relationship. So generally, the gas law, the purpose of the gas law is try to determine the relationship between some of the parameters of the gas. Remember, we have 4 parameters to determine a gas, which is a pressure, volume, temperature, and the mole of a gas. Right? We have 4 different parameters. So here, the Boyle's law is talking about, okay, since we have too many parameters to determine a gas, this is not good if you're changing everything, right? If you're without a constant, then it's really hard to determine the one to see the relationship straightforwardly.
So that's why Boyle
he to determine, okay, we're going to make sure temperature and mole of gas is a constant, which means no change. This is a constant, which means no change. When we determine the Boyle's law, we need to set the temperature and the moles of gas is constant. Well, we know that if you set temperature as a constant, it's pretty straightforward, right? Okay, right now the current condition is temperature constant.
How do we determine the gas, moles of gas is a constant? In what way we can use the moles of gas as a constant? What do you think? Trap the gas in a balloon or something, right? So the inside of the balloon for sure is constant, right? The gas is constant because the gas molecules is just trapped inside. It's not going anywhere. That makes sense, right? Yeah. So in this case, so it's still be able to do this. And then since those are constant, there's a constant, the leftover is just pressure and volume. So they're just trying to figure out the difference, the relationship between. So Boyle's law is talk about the relationship between pressure and volume. So they talk about if we change the pressure, how the volume change. Okay, so this is what happened. If we change the pressure, if we increase the pressure, what is the volume change? If we decrease the pressure, how the volume change? So this is talk about the relationship between pressure and volume. So I'm going to show you one of the demonstration so we can learn it.
In a demonstration of Boyle's law, we'll place a balloon in a vacuum bell jar. We'll apply a vacuum which basically pumps out the air in the bell jar. The pressure outside the balloon will be greater than the pressure inside. The balloon expands to try and equalize the pressure.
Well, actually, I think he did a wrong. He talked about wrong. This is a jar, and they are applying, which means they're sucking the air in the outside of the jar. Okay, which means that the air in the outside of the jar is getting lower. So the pressure inside of balloon is larger than the pressure of the outside of the balloon. So the jar has a less pressure, and the balloon inside has a bigger.
So that's why they are starting expanding. Like where?
Volume and pressure are inversely related to each other. When we release the vacuum, the pressure increases and the volume decreases. As another demonstration of Boyle's law, we will put a marshmallow peep into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the peep will expand to try and equalize the pressure. When we release the vacuum, the pressure increases and the volume decreases. As another illustration of Boyle's law, we will put some shaving cream into our vacuum jar. The shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
So this is a technically, it's just a Boyle's law. Okay, let's talk about the relationship between volume and the pressure. But here is it, we're changing the parameter is pressure, and then the volume will be changed by changing the pressure. It's not a go opposite way. It's not a we changing the volume, then how the pressure change. It's talking about we change the pressure, how the volume change. Are you clear? So here, pressure and volume, which one is independent? Which one is dependent?
Pressure is independent, volume is dependent.
Yeah, pressure is independent and volume is dependent. Volume is depends on the pressure, right? You're changing the pressure, then you're changing the volume. So the relationship is if you increase the pressure, obviously the volume will decrease. And you decrease the volume, decrease the pressure, the volume will increase. So that is the relationship. And how can we put this in a mathematical expression? Okay, how to put this in a mathematical expression? The relationship is just the pressure and your time volume. That's going to be a constant. Okay, pressure and the time volume is equal to a constant. This is a mathematical expression for the Boyle's law. Okay, pressure, time, volume equal to a constant. Or you can write the volume is equal to a constant divided by pressure. You can also write like this, but the most of cases people write this one to represent Boyle's law. Okay, pressure, time, volume equal to a constant. Pressure, time, volume equal to a constant. So, but if you're talking about, okay, if we changing the pressure from 1 atmosphere to the 2 atmosphere, and the volume is gonna change from like a 500 milliliter to what volume, then how do we do this? Most of the cases, people using another equation. It's just P1 times V1 equal to P2 times V2. This is also how the people do this. Since P times V equal to a constant, so the P1 times V1 equal to a constant, P2 times V2 equal to also to a constant, and those two constants is the same. So that's why the P1 times V1 is equal to P2 times V2. Okay, so that's why you can using this equation for solving a problem. So let's move to our study guide, the page 15. Page 15 under the Boyle's law. Page 15 under the Boyle's law. And let's looking at the question number 1 over here. Question number 1. Page 15. Question number 1. So they give you these parameters, and when we solve the Boyle's, when we solve the gas law, I strongly recommend you list those parameters. Okay, it will help you a lot. I mean, you're gonna list your parameter list. So now we have first the volume, that's a 22.5 liter. And first pressure is 748 millimeter height of mercury. And the second pressure is 725 millimeter height of mercury. And the question asking for the second volume. Okay, so if you're looking at here, the given numbers is just a volume, pressure, right? So generally, you're just need to using this equation to solve a problem. So P1 times V1 equal to P2 times V2. So we're looking for V2. Obviously, the V2 will be equal to P1 times V1 divided by P2. V2 equal to P1 times V1 divided by P2, right? Then if you list the parameters, that's going to be much easier for you. So you can just plug those numbers into the equation. That's it. So the P1, 748 millimeter height of mercury, and time V1, which is 22.5 liter,
and divided by P2, which is 725 millimeter height of mercury. And you will see the pressure and pressure, the same unit is cancelled. Left over is just liter. And by the way, I need to emphasize over here, when you do these questions, the unit should be exactly the same. If you're changing the pressure units should be same. If one unit is millimeter height of mercury, the other one is atmosphere, then you have to convert the unit to the same unit. Then you do the calculation. Are you with me? Okay. So you use a 748 times 22.5 and divide by 725. The answer should be 23.2, and this is in liter. Since this give you the unit liter, then you should have the liter over there. That makes sense, right? Now, now let's looking at the question number 5 over here. So this question number 5, it didn't give you a number. This is a kind of like conceptually helping you to understand. So here talk about what will happen to the pressure when the volume is triple at the constant temperature. So what happened for the volume when the pressure is triple?
When the volume is triple, then what is the pressure will be equilibrium. So again, you're still going to using this equation, P1 times V1 equal to P2 times V2. It didn't give you the numbers, right? So you have to make up some of the numbers, right? You can P1. So if there's this conceptual question, if you didn't give you any number, it just made up some numbers, right? So if the P1 is just 1, you just assume, okay, if the P1 is 1 atmosphere, and then the V1, oh, sorry, this is, yeah. And the V1, let's just assume we have a 1 pressure, 1 liter, okay? We'll just assume a number. It really doesn't matter, okay? So this is 1 and 1. Now, they talk about the volume is being tripled. So the second volume is tripled. So original is 1 liter, it tripled, becomes 3 liter. Then they are asking for what is the P2? What is the P2? So then you can put it this P2, that should be equal to the P1 times V1 divided by V2. So now you just have the P1, that's 1 atmosphere. And the time V1, that's 1 liter, and divided by 3 liters over there. Then you will see the P2 is 1/3 of the atmosphere. 1/3 of the atmosphere. Compared to the original one, original is 1 atmosphere. P2 is 1/3 of the atmosphere. How much difference? They become, so the P2 later, if you increase 3 times on the volume, the pressure will decrease 3 times. That makes sense, right? Yeah, the pressure will decrease 3 times. So that's it. Okay, so this is inversely related. Pressure and volume is inversely related. Okay, increase 3 times of the 10 or increase 10 times of the pressure, then the volume will decrease 10 times. Okay, so this is generally the relationship between the pressure and volume, and we call this is a Boyle's law. That makes sense? Okay, so now we're going to work on the practice. I'm going to write down the numbers over here. Then you will you can do the practice. Make sure if you leave, it's better to finish everything than you leave. Okay. Page 2, question number 3.
Page 3, 2, and 3. Page 4, question number 6. Page 5, 7. Multiple choices. 1, 2, 3. Six. Four, six. Okay, so this is the numbers that we're going to practice.
Oh, by the way, I think that it's better you work together with another person. And then you can discuss. This is a much better for just you work alone. Okay? Yeah, if you can find somebody you want to work with, that's much better. Well, yes, that's gonna be the goal side, and then you put using the best methods to solve this. Since there's a number, that's all the number, right? So once you figure out which numbers are here, and then you can get the distribution. This number was this number was this, right? And this number was this number was this. And then you accept this. And make sure every you can put on the left side, and remember on the right side.
Oh, I'm seeing it. Just like that.